So in theory, this thing is recording. All right, guys. Not this supposed to get like a light on the other side of the camera when it's actually doing something? I hit record. That camera is like $300 or something. It's a bit trouble. All right. Well, people listen. Too bad. Okay. Well, thank you guys for coming. This is a smaller group. Yeah, we missed 2 lectures early in the semester, so I felt like we should do something to make up for a little bit lost time. So essentially what we're going to do, we'll keep today's lecture a little bit shorter, and we're going to, basically there were a couple of the last lectures we didn't quite make it to all the way to the end, so we're going to kind of clean up some missing material from the last couple of lectures and get it set up for the next one. And so that's our goal. Before we get started, any questions from you guys? Any either conceptual, procedural, anything about 683 yet? We can have a discussion in here. It doesn't have to be lectures, only 5 of you. All right. Well, to pick up where we left off, remember we're talking about the space of differential k-forms, right? We had this notation, which was omega k, right? And so these were the space where you assign 1 k-form per point on your manifold, right? And roughly, we can, on a surface, right? Remember, we only have 0 forms, 1 forms, and 2 forms. And in the theory of differential geometry, all this primal dual stuff doesn't matter, right? That was what we did in the discrete side. Okay. So in the theory of differential geometry, remember we had, so one thing, are there 3 forms? No, right? You're pretty good at that. So if we want to go from k forms to k plus 1 forms, what operator do we have? D, right? Differentiate. Yeah? So we have this, it's called, I always confuse with chains and there's cochains, I always get which one's backward. And in this case, remember, like if I took a star of a 1 form, and this is, let's say, on a surface, sigma. If I take the star of a 1 form, what do I get? I get 1 form, right? So you can kind of think of it like that. And if I take the star of a 0 form, I get a 2 form. If I take the star of a 2 form, I get a 0 form. Right? So that's the way to think about this, is you have all of these different operators, right? D, star, and so on. And essentially what they're doing is they're moving you into these different spaces of forms, right? And D is roughly derivative, and star is kind of like swapping a plane with this normal and so on. Yeah? That was our basic setup. Yeah? And remember that you can get almost all of the kind of differential little operators that we care about in differential geometry. You can actually get from kind of just moving around in this big graph. And what's important, remember, like for example, the Lopatian takes in a function and outputs a function, right? So we better be careful how we do this, right? Right. So in particular, remember that the Laplacian, we ended up with this expression like star d in kind of a nice mnemonic or kind of way of thinking about this graph, and double checking that you do the right thing. Right? Is you say, okay, well, if I start with a 0 form of the function, I do star, gets me over here. Oops, did I already do this one? Yeah, oh, so read it for the right tool. Duh. Because you're playing too quickly. As you do D star keeps in the same place, and then you have another D here, and then finally have a star. So notice that we took a complete loop in this graph. Okay? This is like a pretty common pattern in deriving kind of interesting differential operators on surfaces. Right? So then we moved into the discrete world, and what we noticed is that actually the discrete version of exterior vectors is easier in a sense than the smooth stuff, right? So now we had 0, 1, and 2 forms, but we had to have primal ones, right? And the primal 0 forms, remember, sat on vertices. The primal 1 form sat on edges, and the primal 2 form sat on triangles or faces, right? And then what else do we have? We have this dual mesh, right? Right? And what dual form sits on vertices? You remember how this goes?
The phase, the 2?
Yeah, it's a 2 form. Exactly. And 1 form, so they go in reverse order. Yeah? So remember what the D operator does is still the same. Right? It keeps you in primal or dual, and it just increases where you're at. It does that just by subtracting. Right? And similarly here, so D goes like that. So these are the D's. And then now the kind of interesting thing, and what distinguishes discrete exterior calculus from exterior calculus, is that the star operators flip you from primal to dual, right? And sort of in doing so, these guys, in this gives you this nice consistent picture, right? Because somehow, if I wanted to go from primal 0 forms to primal 2 forms, I'd have to find some way of taking one number per vertex and making it one number per triangle, and that's like kind of a tricky matter, right? But as long as you just stick on the vertices, then it's just a question of multiplying and dividing by area weights. Okay? This is this really elegant little picture, and you know, we have this nice expression for Laplacian, and somehow everything kind of worked out, right? So again, if I wanted the Laplacian, remember this is star D, we read it from right to left. We start on the 0 form. What happens? You take the star, I keep doing this bad. You start on the right hand side, so you do D star D star again, very simple, right? Even though now there's this vertical part of our graph. Yeah. That was the picture we drew. And if you recall, defining exterior calculus on a mesh is actually really not so complicated. So maybe we'll do a little bit of review because I feel like this stuff is kind of complicated. Just contradicting myself. Oh man. But in practice, it's really not so bad. So I rushed through this a little bit last time. Right. So remember in discrete exterior calculus, we don't store K-forms. We do not. There is such a thing as finite element exterior calculus. That is a thing, but it's kind of complicated. But here, rather than storing like a pointwise estimate of a form, we store it integrated over different places, right? So it's discrete primal 0 form will be integrated over vertices. The discrete primal 1 form is integrated over edges. And the discrete primal 2 form is integrated over triangles. And like we have in this picture, we know how to go the other way. Yeah. And then what we noticed is that if, for some reason, somebody had managed to give me, for example, a primal 0 form, and I wanted D of that integrated along the edges, I could compute that without approximating. Do you see that? That this is, if I wanted the integral of d omega, right? This is because we're looking to figure out how to approximate d. But remember, we never store d. We always store the integral of this stuff. Well, by Stokes theorem, this is a boundary integral of omega. I get rid of this d. Yeah. And well, what is the boundary of an edge? It's just 2 vertices, right? And so it's just the difference of the values of the 2 endpoints. And so I haven't made any approximation here. This d operator, I can actually get exactly, which is kind of nice. Yeah? And similarly, if I want right, and if I want d of a 1 form, it gives me a 2 form, right? So if I have one number per oriented edge, what do? Well, I say, okay, well, what I really want is the integral of d over this form of the triangle, right? That's what I do in discrete exterior calculus. I again apply Stokes theorem to move that d to a boundary operator, and now I realize, well, what is the boundary of the triangle? It's just the union of the 3 edges, right? So if I want to integrate over the 3 edges, then just sum these 3 values.
Okay. Why is it minus W2?
Ah, excellent question, yeah. So the idea here,
the orientation.
Exactly, the orientation matters here. So the orientation of the edge disagrees with the orientation of the triangle. Yeah. This is applying a general fact, right? Which is if I integrate a function along a curve in one direction or in the other direction, I get minus. It's like flipping the normal to a surface. Cool. Yeah, and again, to repeat myself, really, we haven't made any approximations here. This is if you somehow had an integral of a form, you could get integral of d of that form very easily. And remember, we checked that like d squared equals 0. But of course, this d squared is a little bit funny, right? Because really, you should think of this as going from 0 forms to 1 forms to 2 forms, right? So the first d and the second d are different. Yeah. Which is also true in differential geometry, by the way, you know, right? Like the first d takes as input 0 forms, the second d takes as input 1 forms. We just kind of think of it as operating on this giant pile. Yeah. Okay. And then our Hodge store, the idea is that we're going to flip from primal to dual meshes, right? And the way that we do that is essentially, remember, we have kind of integrated things over like 0, 1, and 2-dimensional pieces of our surface. And our job is just to kind of use ratios of the size of the elements to estimate the integrals over different pieces. Right? So, for instance, you know, primal 2 form sits on the triangle, and it'll become a dual 0 form, and so on, right? But the edge is a special case, which just flips, right? Because 2 minus 1 is 1. All right, and this is where we get approximation. So for example, if I had the integral of something over a triangle, and I just wanted the value at the center point of the triangle, the most obvious thing to do would be to just divide by the triangle area. So in fact, the star matrix that goes from primal 2 forms to dual 0 forms, this is annoying, just divides by the area of each triangle. Notice that all the star matrices are diagonal matrices. So nice. Yeah? And then the trickier one is to go from the primal 1 form to the dual 1 form. And I feel like my explanation last time, as usual, could have been improved. If we could teach every lecture here 3 times, that would be ideal for me. But remember that we proved at the beginning of the last lecture that the star operator rotates by 90 degrees. Right? That's its job in life. Yeah? So think about what happens. I have the integral of a function over some edge. Okay, this is like the primal edge. And I have some dual edge that's sitting orthogonal to it. 2 things happen. One is that I rotate by 90 degrees, but just by switching from primal to dual, I kind of took care of that. Right? So what's missing is that, well, I have the integral of a function over this long thing, but this edge might be a shorter length. So I have to multiply by kind of the ratio of these lengths, just to say that I divided and multiplied by triangle area. It's the same trick here. And so what I want is the ratio of primal edge lengths to dual edge length. Yeah? And there's really no God-given way to do this. I mean, because you have to define, so something that we've been kind of fuzzy about so far is like, when I show you this picture of this primal and dual mesh, I haven't told you like, where is this vertex, right? It's just like kind of topologically somewhere inside of this triangle. To define the Hodge-star, we really do place that vertex, right? And in particular, different people have different placements of it, but a really nice one, for the purpose of exterior calculus, is to notice that, let's say I have 2 adjacent triangles, and they share an edge, okay? Well, if I have a form that's kind of parallel to this edge, what I'd really like is for the dual edge to really be perpendicular to it, right? And because that way when I apply the Hodge-star, all I have to account for is the change in length, because we know the Hodge-star just rotates, right? We have to account for the change in length because we're talking about the integrated 1 form, yeah? So what I'd really like is to place points so that they end up on kind of opposite sides of this edge, yeah? And I might as well place it in the middle of that edge, because I don't really have anywhere else to put it. Does anybody know what this is called? If I take every edge and I just divide it in half, and I did it kind of incorrectly. Right, because these triangles all share faces with some other triangle, right? So what I want is if I take any edge, I divide it in half, and I take the perpendicular, conveniently, those 3 altitudes meet up at one point. You remember what that's called? This is all of your high school geometry going back to kick in. Close. This is the circumcenter. Yeah, just unfortunately not the same. Remember, you learn all these different centers of triangles. So this is the one where, oh god, I'm gonna fail at this. If I draw a circle around my triangle, pretend like that's a circle, then this will be the center point of that circle. And one thing that you could check, and in fact you will check on your homework, if you have 2 adjacent triangles, and you look at their adjacent barycenters, and you draw a line between them, they form a 90-degree angle with the center. So that's sort of a very natural choice. Right. And so in your homework, what you'll do is you'll say, okay, let's say I have 2 adjacent triangles, and I pick their 2 barycenters. Now, remember what I need. I need the ratio of the length of this edge to the length, to the distance between those 2 barycenters, right? That's concretely what I need. What do you think that looks like? There's no reason why you'd be able to estimate this, but just somehow we know, secretly at the end of the day we're going to be like approximating Laplacians with this thing, and we get our pluses and minuses in the Laplacian from the d's, but we're missing out the cotangents, right? And in fact, what you'll show is that the ratio of this length to that length is equal to 1/2 the sum of the cotangent of these 2 angles. So no matter what you do, all roads lead to Rome here. You might think that you're in some other regime, but yet again, you get just another Laplacian. Great. Yeah, and that's exactly this. Thankfully, Keenan is drawn much more nicely than I have. So these are the 2 barycenters, and this is the picture they look at the end of the day. In fact, Fernando de Goes and his colleagues have this whole series of papers. They notice that this isn't the only point I could have chosen that has this property that is orthogonal to these three edges. For example, like if I took this point and I moved it along this edge, then I get a different circumcenter, right? And so they work out what they call weighted triangulations, where they sort of put a weight at every vertex that controls where this intersection point is. And for each one of those, they get a different Hodge term. This allows them to optimize some properties of the Hodge term that can be useful for certain applications. Right. So that's, I think, the most complicated part of construction of discrete street calculus. But that's actually not so bad. So, for instance, to go from primal 0 form to dual 2 form, you divide by, you multiply and divide by the area associated with that vertex. Going back to Danielle's comment, in this class, when you've done finite elements and so on, you use barycentric areas, like just 1/3 of the area of each adjacent triangle. Notice that that's actually kind of inconsistent with the story that I've just told you, right? Because I've now drawn this new polygon that's orthogonal to every edge, and this point isn't the barycenter, it's the circumcenter, right? And so, in fact, there are a lot of different ways to do it. I mean, you could just have an inconsistent Hodge star that's somehow inconsistent with you could have a Hodge star for 1 form and a Hodge star for 2 forms that are somehow inconsistent. And it turns out, kind of convergence-wise, that's okay. So for instance, the barycenter, right, where you just take the 3 vertices and you average them, will give you a polygon like this. But notice that that doesn't meet at 90 degrees. Or you could really, honest to goodness, work out the formula for the area of this other dual polygon if you wanted a completely consistent picture of the world. And people do. This is called the Voronoi cell. Any guess as to why it's the Voronoi cell? This second region here. Right, see, this is a circumcircle. Remember, the Voronoi diagram is like the set of points that are closest to this vertex than to any other, right? And one thing you show is that this dual polygon is exactly the Voronoi cell corresponding to that vertex B. And so what you would need is the area of the Voronoi cell, which, as you can imagine, is not a particularly pleasant thing to compute, but you can do it. One issue that people have is like you have a lot of obtuse triangles, you can end up with like really bizarre like negative areas and so on, like things that you really don't want to have happen. So for instance, like here, this thing is like taking a little piece out of the area of 2 triangles away. Something that gets complicated fast. So then people do things like mixed cells, where they say, okay, well I really want the Voronoi cell because it's somehow the best quality, but maybe I snap a vertex if it goes too far, too crazy. This makes sense, right? Because think about the circumcenter of a triangle, right? Like if I have an obtuse triangle, and so he looks like that, right? What is the circumcircle for this guy? Well, it's like somewhere up here, right? And so somehow, you know, when you're defining this polygon, something really funny happens, right? You bisect and like, I guess it's not that far up, but it's outside of the triangle, and you start getting negative numbers that you don't expect. Notice this is somewhat similar to the issue that you guys saw in your homework in finite element. Obtuse triangles really get in the way. Okay, great. A similar piece of research from the same group of people that's worked on these guys. So anyway, at the end of the day, we get this nice complex, right? Here I've drawn it for you in a tet mesh instead of a triangle mesh, but the concept is exactly the same, right? And essentially, what you do is, for every one of these arrows in this diagram, you build up a new matrix, right? And then you start writing down your differential operators as just composition of all of these matrices, right? This is simultaneously easier and harder than just coding a finite element stuff, right? Each one of these matrices is very simple, but you have a lot of them to keep track of. Right. This all supposed to review anyway. And then, of course, the disappointing thing that you'll see on your homework is that at the end of the day, you get the same Laplacian matrix back. But it gives you other operators. So for instance, as I mentioned before, you can get the Hodge Laplacian on one form. Like if you wanted to know what a Laplacian is for vector fields, you can get that by following loops that begin and end on one form instead of 0 forms. And what you get is a nice operator there. So this is a somewhat more general piece of machinery. In fact, oops. The most general formula for a Laplacian on K forms is what I've shown you here. And this will work on any dimensionality, on any form. Yeah, it has all the nice properties. Okay, so this is kind of where we left off. One question you should ask, though, remember that like a large inspiration for why we were doing this was vector field processing. like direction fields that like are guiding placement of hair or used to study weather patterns on the surface of the Earth or whatever. And somehow this machinery is a very nice, unambiguous way to understand how to like differentiate and integrate these things over a surface. But sometimes you want to just look at the vector field. I mean, I actually haven't told you how to do that, right? Like, if you just look at a discrete one form, it's one number per edge, but that doesn't actually really indicate to you the direction of that one form particularly well, right? And so typically the way that we do that is there's something called a Whitney form, which happens to have this form here, but it doesn't really matter a whole lot except to say that the idea of a Whitney form, remember in finite elements we had hat functions, like one number per vertex, and a hat function took one number per vertex and interpolated it into the interior of the triangle. This does the same thing for vector fields. It takes one number per edge as a K form and interpolates that form to the inside of the triangle, right? But like as an actual differential form, right? So you can see that here what they make use of is essentially just the gradients of the hat functions again. This is like the finite element version of the hat basis. And this will allow you to actually read off the vector direction. So the formula here doesn't matter a whole lot. This is mostly just to acknowledge that at the end of the day, even if you do discrete calculus and you're using this for vector field processing, you really can go back and get some notion of vector field inside the triangle. Okay. So as one quick application of this stuff, I thought I'd mention the Helmholtz-Hodge decomposition of a vector field. How many of you guys have seen it, that Hodge decomposition, like calculus class? I think sometimes you prove it on the plane. And that's not so complicated. But in general, if you take any vector field on a surface, you can decompose it as the sum of three vector fields. Typically only two. In most classes you can ignore the third kind. Well, you shouldn't. So one of them is divergence-free. Remember, divergence is like a measure of spreading out. So a divergence-free vector field just circulates. One of which is curl-free. This is the opposite, right? So you can think of one of these kind of like magnetic part and an electrical part, right? So a curl-free part only ever spreads out, or it goes in, it doesn't circulate. And then a harmonic piece, which kind of goes around holes, right? And so one question that comes up in a lot of different places is, can you take a vector field and decompose it into these three pieces? Right, so for instance, maybe I'm looking at weather patterns and I want to find like the eye of the storm, right? And I expect my storm to be kind of circulating about a particular point. You know? Well, how can I do that? Well, remember that we have formulas for div, grad, and curl in exterior calculus language, right? In particular, if you remember back from our table here, what you can end up with is the following, right? That you have, in the fancy way of writing the Helmholtz-Hodge decomposition in the notation we developed here, is that, well, so if you remember, a curl-free vector field is the gradient of a function. This is the fun fact you should remember from calculus class. This has to do with, remember, d squared equals 0, and d looks like curl. Anyway, so what do you get? You get omega, which is a one form, which is a general vector field, is equal to the sum of d alpha, right, which is like the gradient of a function, plus the codifferential of beta, remember that's star to star, plus gamma, and gamma is harmonic, so it has both 0, div, and curl. Yeah? So this is just a fancy way of notating the Helmholtz-Hodge decomposition in the sort of the formalism that we developed. So here's a really nice thing. We have an entire structure for dealing with this stuff now. And what we can get is not an approximate Helmholtz-Hodge decomposition. So like, if I were doing this in finite elements, what I would do is say, well, I have, maybe one vector per face, and have some notion of gradient, and I kind of find the best fitting div, grad, and curl. In discrete exterior calculus, we can get an exact Hodge decomposition in this structure here. So in particular, so what am I going to do? Well, I have a vector field which maybe I represent as a primal one form, right? So I'm going to say this is d of something. So this is going to be d of a primal 0 form plus star d star or something else. So what does that end up looking like? Well, if we work backward in our star, let's say I have a dual 0 form. What happens? Star d star d. D or something. Oh, I'm sorry. Not star D. Sorry. I take D and then star here. Sorry. So we can get. Notice what happened. I have two different 0 forms, but I'm going to represent them different ways, and they both end up in the same place. And then plus the gamma, which sort of says no matter how I go on this loop, I get 0 when I apply it to. Yeah. And the kind of funny thing is, this now becomes a linear algebra theorem. This is just rate nullity. Do you see that? Like you can take any vector and decompose that as like the image of a matrix plus something in its null space. That's all that's happening here. So I can say, well, this is the image of something plus another guy in its null space. Now I decompose it as the image of something else, d star, that remaining part. And what I'm left with is harmonic because it's sort of from both of these directions. You get nothing interesting. So this complicated theorem from vector calculus just becomes linear algebra in the discrete case, which is pretty nice. At the end of the day, how could you do this? Well, one thing you can notice is if you apply the co-differential to both sides on the top here, what do you get? Well, remember, if I apply the co-differential to gamma, you get 0, and so on. Right? Like essentially, all we're doing is saying, well, div of curl equals 0. This is a fancy way of writing that kind of stuff down. Right? So now I have a linear system of equations for alpha and beta, and then gamma is just the remaining piece that after I subtract these two. Yeah? And so at the end of the day, this is like kind of a slick way of doing the Hodge decomposition. Right? I get it from two solves of linear systems. And what comes out is a nice decomposition of vector. Right. I think I'll skip this. Something you can also do is check, like, if I want the eigenfunctions of the one form Laplacian, like d star plus star d star d. One thing you can actually check is that the eigenfunctions of that operator are exactly d. They come from two places. They are d of the eigenfunctions of the zero form Laplacian, and star d star of the eigenfunctions of the two form Laplacian. And you can show that no other eigenfunctions exist. So in other words, like if you want to do kind of Fourier analysis on vector fields, and you use this particular operator, what you're really doing is Fourier analysis on the div and curl parts separately. That's the takeaway. So anyway, all this kind of the nice thing here is that even though this complicated notation, these are all just matrices. And essentially what discrete series calculus applies you are sort of nice decompositions of vector fields and integrable things without having to go too crazy dealing with really crazy operators that happen in differential geometry. So some recommended reading for like applications of this stuff. Actually, there's a really cool survey where what these guys do is they actually manage to, the survey is all the way at the bottom, and they have this moving clock of all of the different people that have managed to find uses for discrete Helmholtz-Hodge decomposition. And it's really impressive, all the stuff that they've done, right? And they even categorized it based on graphics and vision, physics, math, vision, robotics, imaging, astrophysics. And these are all just numerical engines that make use of the same piece of machinery. So this is mostly just convince you that this stuff is actually quite useful when you start, understanding vector fields as composition of div and grad and curl. Yeah. So for instance, here they use it, as I mentioned before, well, I have some noisy estimate of a vector field that's telling me the circulation of a hurricane. I'm trying to find the eye of the storm, right? But then I don't really expect the wind in a hurricane to have that much divergence. It mostly just spins around, like because of conservation of mass. Like you don't compress gas that much. So maybe what you do is you compute the Helmholtz-Hodge decomposition. You just pull out the curl part and you analyze that. So you can get a much more clean signal that way. Similarly, people in fluid simulation worry about this quite a bit because, of course, typically when you simulate water and smoke, this has no divergence. It's just curl, right? And so you can kind of work out like what are the degrees of freedom in your actual simulation by tracking your way around this exterior calculus table. And then people in vector field editing have all kinds of nice ways of editing. So, like for example, if I don't know why they chose an ear, but typically I want to put like hair on the top of the head. And some people's hair has a particular circulation to it, some people's hair just falls backward, and so on. And so you might want to come up with filters like add curl to this vector field, like make my hair more curly. And that's quite simple to do inside of this context. Let's see here. In physical simulation, we'll use it to separate turbulence from acoustics. Right? This is the difference between curl and div. Or to analyze things like I guess if you have diffraction optics, you're looking at some crystallized object at sort of, right at the intersection where this stuff is what you end up with. These nice circulating vector fields that come from your signal. You're tracing stuff moving around inside the vector stuff. I won't even claim to understand quite what's going on in this paper, but I encourage you to look at it because it's kind of cool. And finally, in machine learning, people are actually starting to think about this stuff for vector field valued data. right? So essentially, you know, when I'm studying things like, you know, motion of a crowd in some, you know, so I'm like tracking, for example, the what is it, the presidential inauguration, and I like to track the motion of people. I'm told that was an easier problem this year than a couple of years ago. And then I can use sort of these decompositions as some way to, you know, sort of do machine learning on these separate pieces of the curl, the div in the curl of your vector field, because somehow those are geometrically the most meaningful properties. Finally, just to mention some other kind of extensions of this stuff, and then we're going to do a little bit of cleanup and be done for the day. One question, there are a bunch of different questions you guys should ask. This is going to, thank God, end our discussion of exterior calculus, and we're going to go back onto the countable graph again. Some questions you guys might ask, for example, if you took the graphics class in last semester or previous years, right? In graphics, typically, Trianglebased is only one representation of surfaces. We also have things like Subdivision, which add more and more detail of the surface as you subdivide triangles. And you might ask, like, can you get the nice structure of discrete exterior calculus to work on for example, a smooth subdivision surface? And this is a topic of some recent research. So again, you see Fernando's name a lot in this book. Here he's developed a piece of machinery for exterior calculus that he calls SEC, or Subdivision Exterior Calculus. That's designed for this kind of surface. You can see, so here he uses exterior calculus to compute a Laplacian and parameterize the surface. So here this checkerboard is like, you put a checkerboard on the plane and then maps it to 3D. And you can see that by sort of using the right version of exterior calculus for the subdivided surface as opposed to just this very coarse triangulated mesh, you get a much better result, right? Like the distortion of these squares is a lot smaller. Yeah. The other thing you might ask if you're a mathematician, I think most of the math students in our class are not here today. All of discrete exterior calculus is about asymmetric or antisymmetric tensors. Right? We spent all this time talking about k-forms and how if I swap the input to k-form, you get minus. There are symmetric tensors in differential geometry as well. Right? Can you guys think of an example of one of these? The first fundamental form, right? Like the dot product operator. If I flip the input to the dot product operator, I get the same number back. I don't get minus that. And the question you could ask very reasonably is like, well, can I take derivatives of those tensors? What can I do with those? That's very important in areas of physics, right? So, for instance, the greens, like stress and strain tensors and so on, don't have to be antisymmetric. And sometimes you want to understand how to process those. The answer is, it's really complicated, and this is actually an open research problem. So this paper manages to work out the complete picture for two tensor fields. This is both antisymmetric and symmetric two tensor fields on triangulations in the plane. And it's only in that case, and this paper just came out about 2 or 3 years ago. So if you guys are mathematicians, you like to puzzle over some really, really hard problems. Somehow the really beautiful structure we have in discrete exterior calculus, where you know, all you have to do is like keep track of the integral of a form and everything just works out nicely, just doesn't carry over to symmetric tensors, and we don't know what to do. This keeps me up at night. Okay? Right. So tying all the way back to this vector field lecture, as kind of a summary here of the pros and cons. I mean, the pros here are that it's a very elegant way to store things like vector fields, scalar functions, and so on, and you have a very simple way of computing things like derivatives, right? Like this D operator is just subtraction, right? It's complicated to think about, but the implementation is quite easy. But on the other hand, like this Whitney-based is a little bit hard to work with if you actually want to look at the vector field. And you don't get a vector per vertex, you get it like per edge, and you don't even get a vector per edge, you get like the projection of the vector onto that edge, roughly, right? And so for certain applications where like what you really care about is just looking at the vector field, rather than doing complicated math, like understanding its topology, this maybe isn't the best way to go. So this is one of many examples of this kind of no free lunch. So now we're going to use up the remainder of our time here, basically covering some bases that we had in this class and we never quite finished. I don't know why this is appearing on the other screen. So one of those was Misha's lecture on vector fields, and another was applications of Laplacian and machines. So we have a little bit of graph back. Luckily, we actually just finished the hardest part of discretizing vector fields, the exterior calculus. In fact, essentially this is a reasonable addendum. It's like sort of what are other ways that people represent vector fields and surfaces, right? And it turns out there are many of them. remember that in Nisha's lecture you learned mostly about the theory, right? All these different ways to differentiate. Right, so in general, when you do vector field processing, you know, kind of unsurprisingly, there are kind of three places you can put them, right? You can put them on edges, vertices, or triangles. And discrete exterior calculus is all about putting vectors on edges. And somehow this makes sense from the perspective that edges are one-dimensional, but it doesn't make sense from the perspective that edges are oriented. Like I can't, this edge, his direction is fixed, and it may not be the same direction as the vector field. And in a sense, that's why we had to develop this very complicated, you know, idea of an integrated one form over the edge, rather than just keeping a direction per edge. Yeah. So as an example trade-off, right? One thing you might say is, well, maybe the easier representation of a vector field is triangle-based, right? Because a triangle has a natural tangent plane, right? It's just the plane of the triangle. And I can place any vector in that triangle that I want, and it's sitting inside of the triangle. So somehow the idea of tangent space makes much more sense for a triangle. Yeah? And so a triangle-based vector field actually is much easier to think about than discrete exterior calculus, right? You just store 3 numbers per edge with the constraint that that vector is orthogonal to the normal of the triangle. Yeah? Remember that we talked about hat functions as being piecewise linear? Right? In other words, I put one number per vertex on a triangle mesh and it's interpolated the triangle in kind of a linear way. We can think of these vector fields, where there's just one vector per triangle face here, as piecewise constant. Right? So in other words, there's one constant vector per triangle face. Yeah? And so what does that mean? Well, it means it's super simple to think about. And for instance, if I want to do something like parallel transport, what I do? Well, if I have 2 triangles that share an edge, I would unfold them like that, and then parallel transport is just like, and then I can fold them back. Right? So all this stuff is very simple. But of course the issue is if you're doing things like, you know, you care about the Hodge location, you care about differentiating vector fields, well, you can't here, right? Because this is discontinuous along edges, right? And when you meet an edge, your vector just suddenly changes. So you have no notion of derivative to speak of. We already saw this once. Remember, if I took the gradient of a hat function, which is piecewise linear, right, then that gradient was the piecewise constant. Right, and so here's kind of a picture of what this looks like, right? So you have some basis per triangle and one vector per face there. And again, like I mentioned, there's this nice notion of parallel transport. Right, so remember that we're going to have to think back a few lectures to the lecture on vector fields. But remember what parallel transport is? Roughly, it's moving tangent vectors from one point to another in sort of the most relaxed way possible. Well, just the same as it's really hard to define parallel transport on a smooth mesh, it's somehow very easy to do it on a discrete one, right? Because what happens in parallel transport? Well, clearly, if you have 2 triangles that are in the same plane, then parallel transport should just be scooting it around, right? So the easiest way to generalize that is, again, you hinge it, you move, and then you hinge back. And this is what we call the discrete notion of parallel transport. Now, one thing you'll notice if you do this, like if I took a vector here, I unhinge this edge, I move it there, I unhinge this edge, I move it here, 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 and back, I actually won't end up where I started, unless the sum of these angles is 2 pi. Yeah? So in other words, this really is a measure of what we call holonomy. And in fact, remember we have a notion of integrated Gaussian curvature, right? That was 2 pi minus the sum of these interior angles. Yeah? One thing you can check is the angle from like the vector to the vector translated around a loop, right? You get something rotated. That angle is exactly the integrated Gauss curvature. It all fits together, right? Because remember the holonomy, like the failure of parallel transport to end up where it started, is a measure of curvature. Yeah? So this is a really nice discrete picture overall. Okay. Right. Oh, we have an animation. I borrowed these slides from someone else. Very good. And so typically, if I have some vector field that is moving around the mesh in a way that isn't parallel transport, what I could do would be to keep one angle per edge, which tells me sort of, well, I could have parallel transported it, and now I'm additionally going to rotate it by this much by going that edge. Right. Yeah. Okay. And so this is what we call a connection. Remember, a connection is a way to make tangent spaces talk to each other. Okay. So there's a paper that's worth mentioning because it's very well known in the geometry world, which is called trivial connections paper. And this is the idea that, like, let's say I want the smoothest possible vector field. So let's say I'm doing vector field design, like I have the bunny and I want to put fur on the bunny, and I want to kind of pat it down as much as I can. And I know topologically I can't pat it down everywhere, but I can try to do a good job. Yeah? So maybe I'm given a couple constraints on a couple triangles of the direction I want for my vector field, and I want it to be just kind of smooth everywhere else. It's a pretty reasonable computation. Well, what's going to happen if I just take, let's say I only give you one vector on the bunny. Like I say on his back, I want the hair to go straight down. And I want to propagate that to the rest of the mesh. Well, we have this discrete parallel transport idea, right? So what could I do? I could just kind of greedily choose my neighboring triangle, unhinge, move it over, choose his neighbor, unhinge, move it over. And what's going to happen is I'll actually get a really bad vector field out of that. It's going to depend on what path I happen to choose from that seed point up to all the rest of them. So what you really like is somehow, okay, well, we know that vectors that are parallel transported around are somehow the smoothest possible, but we know that we can't do it globally. We can't just take a vector and parallel transport to all the other points without depending on the path. Yeah? So what the trivial connections paper does, which is really clever, says I'm going to keep track on every edge of how much my vector field isn't parallel transported. You see that? What I can do is say, well, I'm going to put a vector on every triangle, and I'm going to say, okay, for two adjacent triangles, I could take one vector and drag it onto the other guy, right? And I could look at his vector, and these two form an angle, and they're not necessarily the same. Yeah? So the number that I'm going to keep track of per edge is that angle, the rotation or the deviation from parallel transport of my vector field every point. Yeah? So what the trivial connections paper says is that what I'm going to do is actually choose my connection to be 0 everywhere, as much as possible. Okay? So in other words, for most edges, like let's say that I just fix this one vector here, I'm going to pretend like my mesh is planar and just parallel transport it. We know topologically you can't do that, right? That if you do this, it's going to be path dependent. And so what these guys say is I'm going to concentrate the curvature of my mesh on just a few vertices. Remember the deviation from holonomy is the curvature of your mesh. And what is the integral of curvature of your surface? You remember this one? It's 2 pi times the Euler characteristic. Yeah? So I know that I can't get 0 holonomy. I know that somewhere my vectors are going to rotate. But I'm just going to choose a few places where they rotate and make it 0 everywhere else. And so this is this idea of trivial connections on discrete surfaces. Very simple idea. Is that I'm going to do a trivial connection everywhere that I can and then just concentrate all the bad stuff at like one point. Right? And so what I end up with is this very, very smooth vector field that's transported around, pretending as if the surface has no curvature, that it's just like a map to a plane. And then we're going to say, well, all of our deviation from planarness is going to happen just at one place. It's a really simple technique, and actually is used, I think, in practice. Right, so at the end of the day, the details of this method are very simple. You solve for one number per edge, which is kind of the extra rotation. And what are your constraints? Your constraint is that around every vertex, the sum of these angles is 0 or 2 pi, depending on how you look at it. Right? In other words, like if I take a vector and I parallel transport it around a loop, like around a vertex, I end up where I started. Right? But I know that I can't do that everywhere, so I'm going to just allow a couple vertices to have that not be the case. And that's the idea of this trivial connections. And it's a little bit under constrained, like you could have a couple extra singular razors that you don't care about, so then they solve some of these squares thing that says, well, I really like these angles to be small. The result's really nice. So like here's a bunny, and maybe you specify a few points where you say like, okay, these are going to be the singular points, like where my vector field is allowed to rotate. And then I solve this linear system that I mentioned before. What you get is, again, the vector field cannot, is constrained to not do anything interesting away from these points. So notice what happens. At the singular points, you get like interesting flow, like cycling and div and curl and all that kind of stuff. And away from that, it's just nice, smooth straight lines. This is a very useful modeling tool, right? It's useful in computer graphics, in some areas of, like, for example, diffusion tractography and MRI, where people care about the tracks in the interior of your brain. They can use this kind of machinery to kind of trace out where those tracks are going in a nice way. Okay, and you can double check. Look at the back of the one. They're not hiding anything. As a side note, when you're talking about triangle-based vector fields, one nice thing to think about, which I think a lot of people are actually seeing in their course project, is instead of keeping like a vector per triangle, you can keep track of a complex number per triangle. So the idea is you just map that triangle to the complex plane in some arbitrary way. This is kind of nice because really the space of vectors in a triangle face is two-dimensional. Right? You shouldn't have three numbers there because the normal vector you can't have to be orthogonal to that. This is one kind of way that gets you around that. And that fits really nicely with this trivial connections paper, right? Because essentially all you're doing is playing with these thetas. Okay. Right. You can try and do face-based calculus, like a gradient of, you can certainly compute gradient vector fields. Remember we did this earlier, so if you have like a one number per triangle, or per vertex number, we take the vertex, the gradient of the piecewise linear hat function, what you get is one of these vector fields that we're talking about. Something that's useful is something we call non-conforming elements, where you do finite elements, but you actually have one scalar value per edge instead of per vertex. People in cloth simulation really like this, because let's say I'm simulating a piece of cloth. Remember, a piece of cloth doesn't really like to stretch, it just likes to bend. But if I mesh a piece of cloth with edges going every which way, then chances are it's more like chainmail than cloth, right? Because I fixed the length of every edge, and now the whole thing just becomes rigid. Right? And so one way around that is to put your degree of freedom not on the vertices of your mesh, but on the edges, because there are more edges than vertices. So you end up avoiding some of this locking behavior. And we call this non-conforming elements, because what you get is, yeah, some kind of reasonable interpolation of these values to the inside of the triangle, but they actually don't agree along edges. They can disagree, so to that one point. Right. And we already did this in this class, right? So this is one way to get a perfect face picture. Right. So you could ask this question of, can you get the Helmholtz-Hodge decomposition here? And the answer is actually yes. But you have to be a little bit careful about dimensionality. So particularly the dimensionality of the set of harmonic vector fields is equal to the number of holes. Right? So like here you only have one. You have two. I guess it's 2 times the genus, but you have two, one going this way, one going that way. Yeah? So if you just kind of discretize this using finite elements, for example, maybe I take the gradient of a function, and remember this is star d of stuff, so I can think of this as rotated gradient of another function, right? And I do this in piecewise linear finite elements. What happens? Well, you have 2 times the number of vertices degrees of freedom, and you don't end up with the number of holes when you subtract out from that. In terms of, because how many degrees of freedom do you have for a face-based vector field? It's 2 times the number of triangles. Right? So one way around this, right, if you really want your Euler characteristics to match up, is to say, okay, so remember our discrete theorem was the top here, right? 2 minus 2 times the genus equal to the number of vertices minus the number of edges plus the number of faces. Yeah? If I do a little bit of algebra on that, then I get the second expression here. Yeah? So why did I do this kind of funny algebra? Well, look what happens. I have 2 times the number of faces. This is like the dimensionality of any face-based vector field. Let's say I want to decompose this as grad of a function plus rotated grad of another function plus something harmonic. Well, look what this gives me. V minus 1 plus E minus 1 plus 2 times its G. Yeah? Well, 2 times G is the number of harmonic vector fields, right? So if I can take a set of, let's see here, curl-free and divergence-free vector fields that happen to have these 2 dimensionalities, then I'll get exactly the right dimensionality for my Hodge decomposition. So what set of curl-free vector fields has dimensionality V minus 1? Remember, the curl-free vector fields are the ones that look like the gradient of a function. Well, if I have one number per vertex as a function, right? So if I take the gradient, so the space of functions is on a per vertex is v-dimensional. Yeah? If the gradient, then I claim the space of gradients is v minus 1 dimensional. Why is that? What is the gradient of the constant function? It's 0. Okay? So I lose dimension. Similarly here, if I use the non-conforming basis for my div-free part, then I can get this piece and then it all fits together. So this is a really interesting, yet another notion of duality, right? If I want to have the nice discrete Helmholtz-Hodge decomposition, I should take the curl-free and the div-free parts and actually write them as gradients of different types of functions, one per edge and one per vertex. Kind of funny, though. Right. Or you can actually do the other way. Right, so edge-based vector fields we already covered, and then finally we have vertex-based vector fields. And to me, this is actually the hardest. I mean, it seems like if you trace back the history of geometry processing, people tried this first because we want to put all information on our triangle meshes on the vertices. But why is this difficult? Well, a vertex has no tangent space. It's zero-dimensional. It's not one-dimensional. It really has nothing going for it for vector field processing. In particular, like, what is the space of vectors in a vertex if the surface is like pointing down? It's not so clear, right? Because they have to be perpendicular to the normal. Yeah. In fact, you have to define what the normal is, right? Like, so you're really in some hot water. So people do think about vertex-based vector fields. Typically, what they do is kind of similar to hat functions, like. You have one vector per vertex and then some interpolant that gives it to you all over the triangle. So this gives you some possibility of taking lots of derivatives over the mesh, although it typically becomes non-conforming, like discontinuous in different places. But the vertices don't really have tangent spaces, and things like Gaussian curvature get concentrated at a few points, and this can be difficult for differentiating. The one case where this isn't true is like if I want to do vector fields on the plane. Right? So like I really do have a map of the United States, and I have weather patterns on that map, and I only care about the two-dimensional stuff. Then it makes perfect sense to take a vector per vertex and just linearly interpolate it to the inside. But do you see why you get in trouble if you have a 3D model? Because you have a vector here which is perpendicular to this vertex is normal. You have another vector over here which is perpendicular to some other vertex normal. And how do I interpolate between them? Well, you don't even know what the normal is between two vertices, so it's not so clear how to go about. So in particular, this 3D case is quite important. One way that people have proposed over the years, and it comes up every once in a while, it's something like the geodesic polar map. So the idea here is I take a vertex and I take all the interior angles adjacent to this vertex. These sum to some number that's not 2 pi, right? In general, it's only 2 pi that's flat. So what I'm going to do is just scale them so that they do sum to 2 pi. So this gives me a map of this vertex into some kind of, radial set of lines in the plane. And now what I'm going to do is do all of my vector field processing in this plane and try to avoid ever embedding back in 3D if I can avoid it. Right? This math becomes really complicated really fast. And to me, it's mostly an indicator that you're somehow doing something wrong. But there are some people that advocate it. And actually recently some people have even given some nice kind of interpolated machinery for kind of taking these per vertex fields and interpreting them on the inside using this stuff. Right. Finally, so the big takeaway for vector field processing class here is that vector fields, there's no consensus for how to represent a vector field. That plenty of data really does naturally fall into this category, right? Like flows of fluids, motion of people on a graph, directionality of tracks inside of your brain. All this data looks like a vector field, but nobody can agree on how to represent it. This is yet another instance where somehow the discrete stuff, there's no clear answer what the best thing is. You really have to think about what properties you need. So we talked about the 3 most basic representations of a vector field. These actually aren't the only ones. There's some really exotic ones, in fact, that are actually kind of cool. So one of my favorites, obviously because it extends one of my papers from many years ago, it was proposed at the Symposium of Geometry Processing in 2015. And this actually, I don't know if you've ever read the very famous set of differential geometry books by Spivak, and this is how he defines a vector. He said, it's very similar to we define a zero form as a thing that takes dot products with vectors. He says, well, a vector field is an operator on functions. And the idea is, if I have a vector field, and now I put a function on my surface, then what is the vector field acting on that function? It's the directional derivative of the function in the vector field direction at every point. That makes sense? So what these guys advocate is they say, rather than representing vector fields as one number per vertex, one number per edge, or one number per triangle, I'm going to actually represent a vector field as a matrix that takes in a function and outputs another function, which differentiates it at every point. Okay? Why is this useful? Well, for one thing, you can compose these operators very easily. This is matrix multiplication. Okay? And if the thing that you really care about is directional derivatives, then this representation actually makes a lot of sense. Yeah? The other reason is that remember that you can somehow take functions and decompose them in low frequencies. This is the idea from Fourier. Well, now you can have some notion of a low frequency vector field by taking this operator and just restricting it to the low frequency eigenfunctions in the low Plochner. It's really kind of I would say kind of an out there idea. as they go, but an interesting one. And in fact, for example, Omri, this is the primary author of this paper, has even managed to apply this to like fluid simulation. So they have a follow-up paper where they're simulating, you have like a wine glass, and you know, when you have a glass of wine, you kind of shake it around, and then you get something they call legs, I think, in viticulture, right, where the wine kind of leaves these little drips behind, these special shapes. And they're able to use this vector field machinery to kind of represent that motion in a very elegant way. And kind of a niche application, but it's nice to look at. Another extension of this machinery that's useful in meshing, for example, is to think about direction fields rather than just vector fields. So a vector field assigns one direction per vertex of a triangle mesh, or per point on the surface. But I might, for example, a very common one is to have a four-direction field, right? Or a four-vector field, whatever. So for instance, let's say that I'm doing quad meshing. So I have a surface, I want to cover it with little quadrilateral elements. Then maybe what I do is, as a pre-processing step to quad meshing, I compute a four-direction field over my mesh, which is going to guide where I place this sort of streamlines of this quad mesh, right? And then I go back and just trace out the lines to actually get my mesh. A very common pipeline. So the most general version of this, and a really kind of a fun idea to think about, is something called the polyvector fields, or N polyvector fields, which was proposed just in 2014. This is all relatively recent stuff. And so some of it is really not thought through. There's probably some interesting research problems happening here. So the idea of the polyvector field is like, at every point on the surface, I want to store, say, 10 vectors. And I don't want them necessarily to be orthogonal, I don't want them to be evenly spaced, I just want to store 10 vectors. And I want some notion of, like, for example, if I have 10 vectors at every point on my surface, how smooth is the field of 10 vectors along my surface? It's a tricky question to think about. Right? And what I wouldn't want to do would be to just store a list of 10 vectors per point. Okay? Because, for example, if I had, you know, I have two. Let's say I have two adjacent triangles, right? And maybe I start at sort of 10, let's say I start at 2, right? So I have these two frames. Okay? Some of these are very similar, right? But if all I know here is I have like two numbers, like on this triangle and that, right? These are just a set, like they have no order, it's just a pair of vectors, right? So I want to know how smooth they are, I first have to match this one to this one, that one to that one, and then check that they're smooth. But I can get into trouble, for example, if I go around a loop and the matching is kind of inconsistent. Yeah? So what these guys do is really sneaky. It only works on two-dimensional surfaces, by the way. It's a really clever idea. So they say, okay, remember that I can think of this like A1 e to the I theta 1, right? I can think of this by identifying the plane with the complex numbers, and so on, right? So this would be like A2, and so on, maybe B1 e to the I theta bar 1, and B2 e to the I, whatever. So what they say is, okay, rather than having to store like pairs of vectors and then having to deal with matching them, I'm going to come with a new representation. So let's call right. So here's the complex number of zi. Right. I'm going to define a polynomial, and that polynomial is f of x. In this case, I want to store two vectors, so this is a degree 2 polynomial. Yeah, it looks like x squared plus c1 x plus c0 for two complex numbers c1 and c0, right? Which are not the same as z1 and z2. For example, c1 would be what? z1 plus z2, and c0 would be the product of the two. So what these guys advocate is rather than storing the z's, which are effectively the directions of the vectors, they instead store the coefficients of the polynomial in the plane. And the reason for doing this, so one thing, this is reversible, right? For every polynomial I can find the roots and get these vector directions back. But the nice thing is that this encodes the two directions without having to worry about which direction is which, right? It's just some polynomial that happens to have two roots. Right? So checking smoothness, it makes perfect sense to check whether these coefficients are smooth functions, but it doesn't make sense to check if z1 is smooth because I might have accidentally changed the labeling of 1 and 2 here. You see the difference here? So this is this nice trick, they call this polyvector fields. This only works in 2 dimensions, because in 3D, you don't have complex numbers. Yeah? I suppose it works in even dimension, right? In 4D, you have some level. Anyways, this is an interesting representation for multi-direction field, where at every point you don't want to just store one direction, you want to store one. Okay, so they use this, for example, in quad meshing here, I think, yeah, what they want to do is evaluate how smooth directions of quad meshes are, which may not be orthogonal. So they kind of develop these fields at every point, and they have some smoothness function. They tell them how well they did. Right, so that cleans up vector field processing. And I told you we're going to do a quick grab bag of all the topics we're missing, and then starting next time we'll be back on track for all the topics that we wanted to cover in this class. The last little quick bit that we're missing was we talked about application of the Laplace operator. Right? Remember, that's D star D, the other way around, star D star D. Yeah? And we mostly talked about things like the heat kernel signature and so on that are on surfaces, right? But one thing we kind of neglected to do, and I forgot and moved on, was applications of Laplacian machine learning. There's only a couple of these to mention, and we'll stop it today. Right. So the most simple one of these, that's a very famous paper, and this is a grab bag of topics, kind of cleaning up based on some previous lecture. Is something called semi-supervised learning. So the idea of semi-supervised learning is maybe I have a very large data set, and then over just a few elements of this data set, I have a label. Right? So for instance, maybe I have 1 million images, like I scan a magazine, and so this gives me a picture of every letter of the alphabet a bunch of times. Right? And I add so I have this giant collection of all these images, but only on a few of the images has somebody labeled what they actually are. Right? So the question is, can I infer the missing information? That's what semi-supervised learning is. So one good example of this is like I have a bunch of handwritten digits, and just based on image similarity, maybe I can construct a graph that says like these two are similar, and these two are similar, and so on. Right? And then somebody labels a few of these, like this guy is 1, this guy is 0. The question is, can I infer? Yeah? Well, how could we do this? Well, let's say that our label is some function f of I, where I is what vertex you're on. Right? Then what you expect is for your label to kind of change smoothly along your graph, right? So maybe what I do is along every edge of my graph, I subtract the labels and I want this difference to be small. Yeah? So I square and I sum up. You guys remember what this energy is called? I take a bunch of differences, like d of a function, by the way, and then I square and I integrate. This is called the Dirichlet energy in my labeling function. Right? So maybe I minimize the Dirichlet labeling energy in my labeling function. Well, wij is like how similar are these two digits, right? Well, this is exactly the semi-supervised learning, and what it gives you is a really nice actually technique that very simply, just by solving linear systems of equations, can propagate the label from these 2 points. For example, like here, I think this is 1 and 0, and cut it 1/2 to all the other points of the domain. So this is mostly just a quick note that like these manifold methods that we're talking about for vector fields and Laplacian and so on are not just applicable to 2- and 3-dimensional objects that we have in computer graphics. They also are in very high-dimensional data sets. For example, this Laplace operator here could be a very high-dimensional manifold of images, right, which have parameterized by all kinds of numbers, and still exactly the same machinery holds. Right, this is just a Laplace operator; it has all the same properties. Right. So yeah. So in very closely related method, maybe you use the eigenvectors and just solve semi-supervised problem in subspace. This is a common trick for cutting down your computation time. You should be suspicious of these techniques, because remember what I told you when I solve Dirichlet problems and I have a few point constraints? Then what happens is, yeah, my function is smooth everywhere except at those point constraints, which is exactly kind of where I have information. Empirically, for a lot of these semi-supervised problems, that doesn't appear to be a huge issue. But if you want to be careful about it, for one thing, take a look at this paper, which really analyzes what happens as you add more and more data, and you start to approach this funny singular case. And one potential fix would be to just use a higher order operator. Right? The more times you differentiate, the smoother your function gets. A different context where the similar kind of ideas from exterior calculus, Laplacians, and so on show up in the machine learning world is in regularization. So for instance, let's say that I'm doing some kind of supervised learning problem, right? And so what I'm trying to do is learn some function from a data point x to a label y, right? And typically you have sort of two terms when you optimize these things. This is even true for deep networks. This isn't like somehow outdated in the last 5 years. So the function v is your loss, right? So for instance, like, does the predicted label match the actual label I got? So we have images, I don't know if they're cats or dogs. So the y's would be cat or dog, and x would be the image. And the second one is that I expect my function f to kind of not be crazy in between the data points. Do you get that? So like, what I don't want is like, f is cat on all of my cat images, dog on all of my dog images, and then on any other image that I haven't seen, like, you know, banana. Wouldn't make any sense, right? I expect it to be smooth. And so typically what we do is we add a second term here that just measures how crazy f is. Okay. So think back to our semi-supervised learning paper. Let's say I had this big database of images and a few of them were labeled, and I wanted to learn a function from images to labels. This is slightly different from like building a graph and propagating labels along the graph, right? So I want to build a function from images to labels. That would be my function f, right? Well, the idea of manifold regularization is a really elegant idea. As we say, okay, well, what do I want? Well, I want that my function from images to labels not only reproduces the data that I have, that's its first term, but it's also smooth. But I don't want it to just be smooth on the set of like all possible inputs xi. I only really care about it being smooth on the set of images. Right? That's a very specific kind of manifold that's sitting inside of the space of all possible assignments of numbers to pixels. Yeah? And so what these guys propose is they say, okay, well, what do we want? We don't want the smoothness of f just as this very high-dimensional function. We just want the Dirichlet energy restricted to the manifold of images. Okay? And how could we build that? Well, what we can do is essentially use the graphal portion of the set of images we have in our data set as some notion of smoothness, right? But now evaluating our energy in a set different way, right? So there are many examples of manifold regularization, and I encourage you guys to read these papers because they really are quite elegant. It's a grad class, so I'm not going to read them to you. But essentially the idea here is you have one term for your loss, like here this is least squares, and here this is SVM. And then you have the second term, which says specifically if I restrict to this graph, how smooth is my data set? It's as simple as that energy we had before, it's least squares. Right? And the nice thing is what they're able to prove, these guys, is that not only is this an effective regularizer in practice, so for instance here, it's able to classify the red from the blue with just one labeled data point on each side, because you want it to be smooth on these two sets. Yeah? But also, as you increase the sampling of your data points, this really does approach the Laplacian of the underlying manifold under some conditions. So you really do get the regularizer that you want in the sort of limit of big data. And then finally, and we'll stop here, and just one thing worth noting. We spent quite some time talking about calculus and distances and derivatives and so on metric spaces where sort of the main piece of geometry comes from geodesic distance, like shortest path on a graph. But that's not the only notion of distance. So another one is diffusion. Right? And so there's this big idea in the applied math world called diffusion maps. And the whole idea here is that I'm going to go through a lot of the operations we already talked about, like computing distances between points and so on, and talk about them in terms of Brownian motion instead of in terms of geodesic. So for example, I could talk about like what is the expected amount of time if I have some particle that's randomly wandering around in this space. How much time will it take me to get from A to B? There's some notion of distance that's quite different from the notion of the shortest path, because that particle is wandering around and doesn't know where it's going. And so for certain kind of sampling and noise issues, this is closer to what you want, right? And so for instance, if I want to classify these two rings of this barbell set, then somehow this diffusion model makes a lot of sense, right? Because you can diffuse outward in this circle quite easily. It's very unlikely you'll diffuse along this small map, right? So it's easy to take a signal here and have. So somehow, with respect to diffusion distance, these two sets are very far apart, whereas with respect to geodesic distance, for example, these 2 points might be very close together. Right? How do you think you compute diffusion distance? Well, once again, it's nothing more than just something derived from the Laplacian operator. Right? We know how to do heat diffusion. In fact, you'll do it in your homework. And so computing things like diffusion distance becomes just a linear solve in terms of Laplacian. Or you go into the But anyway, with that we'll stop. So that's our grab bag of sort of missing topics from 6838 that we're going to need that I noticed we kind of glossed over or skipped a bit, which I figured was appropriate for our kind of extra lecture here. starting next time, we're going to talk about a little bit of an in-depth application of all this vector field stuff to an area that is very close to my heart called oscillator transportation. So this is all about matching signals on top of a domain, and what we'll see is that vector fields are going to be our means by which we move signals into each other. So it's actually a very useful topic. And then finally from there, we'll move into, we spent all this time analyzing one shape. We're going to talk about shape collections. How do we put things into correspondence, map them to each other, transfer information from one shape. Then we're done with this class. So with that, we'll turn off the camera, and thank you guys for coming in this lecture today. I'm hoping that the camera will have mercy on us and not delete this lecture. I really should complain to Dell. So I click